So I gave my first talk on EHT results in this room 6 years ago, the day after the press conference. So now I'm going to talk sort of about what have you done for me lately? And this is about what's going on with Event Horizon Telescope now. First image of a black hole here. What's going on now? And what can we expect in the near future? And how do we model these? And how do the models interact with what we can learn about black holes? Okay, so this is the image of the black hole at the center of the M87 galaxy. What you're seeing here is 230 gigahertz or 1.3 millimeter radiation produced by the synchrotron process in a hot gas surrounding the black hole. So this is gas at a temperature of something like 10 to the 10 Kelvin. The Lorentz factor of electrons in that gas is several tens typically. And there's a magnetic field, we think, embedded in this with a strength of a few tens of Gauss. Okay. And this characteristic ring-like shape is difficult to explain in great detail, but I think the basic idea is very simple and can be thought of as analogous to this. So there's hot radiating gas around a completely absorbent object. And that gas is turbulent and fluctuates over time, just like this. And we see a sort of bright edge around the dark object in the middle. Now it's more complicated than this in the case of a black hole, because gravitational lensing plays a significant role in shaping the image that we see. But this is really all there is to it. Okay, so M87, the black hole in M87 is at the base of the archetypal extragalactic radio jet. So the jet can be traced down from many kiloparsec away all the way to the black hole at the base, and I'll show you a few images of that in a moment. But that jet comes out in this direction at a position angle of minus 72 degrees. So this is north, and this is minus 72 degrees. And we think it's tilted somewhat to the line of sight. The jet is tilted at about 17 degrees. And this inclination angle is deduced from a variety of methods from the jet itself. So it's sort of pointing just off the line of sight to us. Okay, so some of the big questions about this system relate to the spin of the black hole itself. And in particular, what powers the jet? Is the jet powered by the spin of the black hole, or is it powered by the energy extracted from infalling material? And that's one of the main things that we'd like to get at in the years ahead with Event Horizon Telescope. Okay, so in addition to working with the people who make the images of black holes, my group builds models of these systems. So we run fluid dynamical simulations of the gas surrounding the black hole. And then we do radiative transfer calculations to produce synthetic images of the black hole. And the results look something like this. You can see the material circling the drain there. And you can see there's a bright ring here and then a narrower ring here, which is related to the effects of gravitational lensing. So in this ring, we're looking at material all the way around the other side of the black hole. Sometimes on lines of sight that follow 2 or 3 orbits around the black hole itself. Okay, so this is the general picture that I'm going to talk about. These images. We want to know about the connection to the jet and to the black hole spin. And one of our primary tools in doing this is simulations like this. Okay. So here's the plan. I don't know what's okay. Here's the plan. So I'm going to start by reviewing the results that have come out of EHT since that first image. And then I'm going to talk about what's next for EHT. So what new data are we going to get? What new capabilities will EHT acquire in the next few years? And then I'm going to talk about one of the most obvious features of that ring I just showed you, which is the asymmetry side to side. So in the north, it's dim, and in the south, it's significantly brighter. And we can investigate that using the simulations, also simple models, but mainly the simulations to understand where the asymmetry comes from. And then I'll just end with a brief summary. Okay, so let's start with the review of results. So this is the sort of rogues gallery of images produced by EHT. The bottom two images are related to the galactic center, which is sort of a whole another talk, so I'm not going to spend much time on those. But the top three images are of M87. And on the left is this first image, which I've already showed you. In the middle is a polarized image. So you can see little striations on this image, which are not features in the total intensity. Those are striations we've introduced to show the direction of the linear polarization on the ring. And that provides information about the magnetic field in the source. So very approximately, you can think of the magnetic field as being oriented perpendicular to these lines in the source. And it's complicated. It's more complicated than that because there's Faraday rotation in the source, which changes the angle of linear polarization. And also there's gravitational Faraday effect, which rotates the angle of polarization if the black hole is spinning. Okay, and then on the right, we have an image from 2018 data, which confirms, thank goodness, that the source is still there. And it's more or less consistent with the 2017 image. Okay, so let me just go through this for a couple of those images and say something about what we learned from them. So this shows the total intensity image, and the key piece of science you can easily extract from this is related to the black hole mass. So when you take introductory relativity, one of the first exercises you do has to do with photon orbits around black holes. This calculation is done in sort of week 4 of GR. What you can learn is that photons that are orbiting the hole emerge at infinity with an impact parameter, which is equal to the square root of 27 times the gravitational radius, gm over c squared. And that corresponds to an angle root 27 gm over c squared d. And then we're talking about the diameter here. So there's a factor of 2. So we have a pretty good estimate of this. And so when we measure this, we can infer the mass. And one of the main results out of this image was that the mass of the black hole in M87 is about 6×10⁹ solar masses, which resolved a discrepancy or an ambiguity in earlier measurements. The gas measurements tended to be at about 3 billion solar masses, and the stellar dynamics measurements tended to be at about 6. Okay, so there is the mass measurement from this image. Okay, so next I want to talk about this image, and compare these, because you'll notice that they look different. And they are in fact different. That difference in the image is statistically significant. So you'll see that the main difference is that the point of brightest emission on the ring has shifted somewhat in a counterclockwise direction. And this was very satisfying to see, because when we wrote the paper about this, we said that based on the models, there's a distribution of position angles for the bright point on the ring. The distribution is sort of Gaussian and oriented around about this angle. And so we said that this was unusually far around on the ring, and that when we visited it again, it was quite likely that it would rotate in this direction. And in fact, that's exactly what happened. Okay, so we think we know something about the source from the agreement of the source with the data, not just in this rotation, but in a number of other metrics, which I won't go into. We have a set of favorite summary statistics that we use to compare the models with the data. Okay, now I want to show you one other image which directly makes the connection between the nucleus and the jet at very small scales. And this image is not from EHT. It's from a collaboration called the Global Millimeter VLBI Array, or GMVA. And this appeared in Nature a couple of years ago. This is a longer wavelength image, so lower resolution than EHT. And you can see down here, there's a hint of a ring at this lower frequency, and then there's a direct connection to the jet. So this shows that the black hole is anchored in the immediate neighborhood of the jet is anchored in the immediate neighborhood of the black hole. Okay, so that's some of the results that have come out of EHT. So now I want to talk about whether there's anything left to see or whether we're done. So EHT has been revisiting M87 and Sagittarius A star whenever possible. So we lost a year due to the pandemic, and we lost a year partly due to bandits at a telescope in Mexico. But we have the first campaign that produced the first image here in 2017, and much of the data from that is understood and published. 2018 is partly out. The 2021 images are in process within the collaboration. And then we have data from a number of additional years. And we just finished the 2025 campaign yesterday. So EHT is continuing to take data and revisit these sources. And especially for M87, this is important because it's fluctuating with time. So if we want to understand what its average state is or the statistics of its variation, then we need multiple uncorrelated observations of the source. And then I just also want to draw your attention to this, which is the plan for 2026. And the idea there is to revisit M87 at regular intervals over the course of the spring observing season and take a set of images that we can use to assemble a movie of a black hole. Okay, so this is the movie campaign. So while all this is going on, and I would say this is all done with spit and baling wire. So EHT people don't ride to the telescope in limousines. We have support from many different countries, which right now is looking like a pretty good arrangement. So we have a diverse set of funding sources, but they are not lavish. So a lot of this is done with sort of volunteer time for members of the collaboration. But anyway, while this is going on, we have added new telescopes. So there's a telescope in Greenland, of all places, at where that is owned by the Smithsonian and instrumented by Taiwan. We have a new telescope at Kitt Peak. So there's an old millimeter telescope there that was refurbished. The Noema array in Europe, and the Koreans are now joining with an antenna. So in addition to this, there are now 345 gigahertz fringes. So these observations are done at 230 gigahertz, 1.3 millimeters. 345 will get us to 0.86 millimeters and significantly higher resolution. Okay, so here's a summary of new capabilities that are coming from EHT. So 345 gigahertz is on the way. Fringes have been detected. It's something that we're capable of doing. This will change our nominal resolution from 20 microarc seconds to 13 microarc seconds. And for the galactic center, that means going from 4 GM over C squared to 2.6 GM over C squared. So another thing that we've implemented is so-called agile observing. So this means being able to go to the telescope and turn on an observing campaign without having a VLBI specialist on site. And this will enable the movie campaign that we are proposing for 2026. Third is the addition of new sites. So most of these are non-US funded. The ERC has funded a telescope in Namibia called the African Millimeter Telescope. And Schmidt has funded an antenna in the Canary Islands, which is partially supported by Spain. So this will enable us to reproduce, to produce higher fidelity images. So every image that we show of the galactic center is one of an ensemble of images, which is consistent with the data. And that's because we don't sample the entire Fourier domain when we make an observation. But if we add telescopes, then we sample more points on the Fourier domain, and we reduce the set of images that are consistent with the data. Okay, and then the final thing, which is super exciting, is going to space. So there's a proposal that's outlined in a paper led by Michael Johnson for an instrument called BEX. This is the Black Hole Explorer. So this would go into middle Earth orbit so that we can observe the one ring to rule them all. And we'll move the nominal resolution from 20 microarc seconds to 5 microarc seconds. Okay, so this is 1 GM over C squared. BEX is a small explorer mission, and NASA. So we don't know what's going to happen, but the development of the proposal is almost complete. Okay, so I just have to show you this, which is a reconstructed movie made with simulated BEX data. So this has gone through an entire simulated observation process from start to finish. And on the left, we see what you would see with EHT. On the right is a simulation, and in the center is the movie that BEX would produce from this. Okay, so you can see you get a lot more information out of the BEX movie than you do out of EHT, although you can still see some evolution from EHT. Okay, and I just pointed out that this is produced by 2 postdocs at CFA, Paul Tita and Daniel Palumbo. Okay, so so this is what we can look forward to, I hope, with EHT. So now I want to go on and talk about the ring asymmetry in M87. Okay, so the key obvious features of the ring, the things that are easy to measure without straining credulity, are the radius, which tells us about a relationship between the mass and the distance of the black hole. So we measure the angular radius. And there's an element here of model dependence in this measurement, because this so-called critical curve on the sky, which is root 27 GM over C squared D, it's not obvious how to place that on one of these low resolution images from EHT. So let me just back up for a second to this. You have to decide where in this ring you're going to put that root 27. And that's uncertain to about 20%. So we use models to try and enable a mapping between the ring that we see on the sky and the sort of mean radius of emission and this root 27 GM over C squared D. Okay, so there is a model dependent uncertainty there. Okay, but then the two other features of the ring which are most obvious and which can be reliably measured in the data are the asymmetry amplitude. So what is the brightness contrast from one side of the ring to the other? This is the sort of thing we measure by fitting a model that has multiple Fourier components. And we extract the amplitude of the m is equal to 1 Fourier component and compare it to the amplitude of the m is equal to 0 Fourier component. So this is something we can do quite reliably. And then the other feature is the asymmetry orientation. So what is the phase of that m is equal to 1 Fourier component on the sky? Okay, so what I'm going to argue here is that the asymmetry amplitude is directly related to the spin. So if you know what the inclination is, if you believe you know what the inclination is, then it seems that the amplitude of the asymmetry is roughly scales with the spin amplitude, so denoted A here. Now there's a significant model dependence in here, which is why it's important to make good models of the source that include our best current knowledge of the plasma physics. But I'll show you a set of models where this relationship is quite clear. And these are best bet models. They include the best bet physics, they include the highest resolution, and they include the sort of half of model space that we think is most likely to correspond to observations. Okay, and then the third feature is this asymmetry orientation. And we think this corresponds to the spin direction on the sky. So the projection of the spin vector of the black hole onto the sky. So this also has some model dependence in it, but I'll show you a little bit more about this in a minute. And these two papers are being written up now. This one is nearly done. This is 2/3 complete. This is led by a terrific undergraduate named Vadim Bernstein. So if you're doing graduate admissions next year, you should keep an eye out. And then the second one is led by my student, Nick Conroy. Okay, so how can we understand the dependence of the asymmetry on spin? So this is actually a really difficult question, which is why you haven't seen this talk before now. And in order to sort of suss this out, we've looked at some very simple models. So I'm going to show you a survey over spin of a steady state model where we have a little ring of emission down very close to the black hole event horizon. And it's not rotating with the full sort of Keplerian angular momentum. It's rotating fairly slowly, which is something that is consistent with what we see in the simulations. Okay, so So this guy has spin minus 0.96. So let me explain what that means. So in all our work, the orbital angular momentum of the accretion flow is the boss. So the orbital angular momentum vector is always pointing up in these slides when we project it onto the sky. In fact, it's at an angle of about 20 degrees to the line of sight. Okay, and then if the spin is minus 0.96, the flow is retrograde. And so the projection of the spin vector on the sky is pointed downward. So then we're going to move the spin up toward positive spin, and then the spin will be pointing upward on the plot. Okay, so let's get this underway. You can see one of the interesting features of the Kerr metric, which is that this ring moves. And I'll go back and show this again. The ring moves and it changes size very slightly as the spin changes. Okay, so here is the negative spin model, and you can see that it's dominated by this region over here in the images, and then we run it over to positive spin, and this interior, which is the direct emission from that unlensed emission or nearly unlensed emission from the ring of material that we've inserted in this toy model is here, and that lights up as we move toward positive spin. And now the emission is dominated by this side. And this is very roughly what we see in the models, in the more sophisticated time-dependent models. Okay, so let me show you something about what's going on here. This structure is pretty obvious, I think, if you think about Doppler beaming. Okay, so this material is rotating around the hole like this. So this is the approaching side, which is Doppler boosted, and this is the receding side, which is Doppler dimmed. Okay, what is less obvious is what's going on here. And so I'm going to show you a little movie now, which should help to explain what's going on here and also explain why this is a little bit complicated. Okay, so this shows is a slightly lower resolution version of the image I just showed you with spin 0.96. So the sort of approaching side of the black hole is over here. Okay, so it's projected down. And then over here, I have the set of geodesics that are traced back from the image down into the model and around the black hole. And these run from the outside of the image here toward the inside of this little band here. Okay, so we're going to watch what happens to these guys as they wrap around the black hole. And you can see that some of the orbits are kind of Baroque here. So some of them involve multiple passes around the black hole. These guys, the outermost one, is less lensed. So it's lensed by maybe 270 degrees. It's deflected by maybe 270 degrees. But some of the others here take an immediate U-turn and head back up through the midplane of the accretion flow around the black hole. And I should say that this image is now done not in this frame, but looking at the black hole from the side. So now the black hole spin is just directly downward. Okay. Yeah. So let's let this thing go and just look at the geodesics as we rotate them around. And you'll see that there's strong lensing in here, which allows the geodesics to pass again through the midplane of the black hole, of the accretion flow, and as a result, increase the intensity along those lines of sight. Okay, so lensing is a key part of the explanation for the higher brightness for the negative spin models on the spinward side. Okay, yeah.
Just quickly clarification. So is this really a ring like that you're using as emissivity, or it's like a extended in radius? Does the radius depend?
Yeah, this was just, you know, Charles sitting around late one night, inserting a simple model, which is a Gaussian in radius. And it peaks at about 2m, which is slightly outside the hole. And then it's got a width of about 1m. So this thing is really down in there close to the event horizon. Yeah. And this doesn't really represent the sort of variety of phenomena that we see in the full simulations. So there are a lot of factors that contribute to this switching of sides and to the amplitude of the asymmetry. Okay. Any other questions? Okay. Okay, so here are some of the contributing factors. So as I said earlier, Doppler boosting is a really important one. This is what turns off the direct emission from this ring of plasma around the black hole as we go from high positive spin to zero spin. Okay, so the Doppler dimming becomes more severe as you turn down the spin because of the direction of the geodesics as they intersect the midplane of the emission. So you're actually, when you go to negative spin, you're sort of looking at the plasma from behind as it's orbiting the black hole. Okay, so that's sort of the worst case, the strongest Doppler dimming. Okay, so this is an important factor in turning off the direct emission from the rotating plasma as one goes from positive spin to zero spin. And then lensing is an important part of turning on the emission on the other side of the ring as one goes from zero spin to negative spin. Okay, but there are multiple other effects here, which is why this is difficult to disentangle. So one is just radiative transfer. So it matters what angle the geodesics intersect the midplane at. So if it's an oblique angle, then you get more brightness on that line of sight. You can integrate up the emissivity over a longer path length. And it also matters what angle the geodesic intersects the plasma at compared to the orientation of the magnetic field. Because synchrotron radiation occurs predominantly perpendicular to the field and not at all parallel to the field. So if the field is well organized, then this can be an important contributor. Okay, and then yet another factor is the plasma flow itself. So many of you probably took some kind of high energy astrophysics course where you learn that accretion disks have a characteristic angular momentum that you can calculate in GR, extending down to the innermost stable circular orbit. And then the plasma plunges into the black hole, conserving its angular momentum and specific energy on the way. Okay, and it turns out that's not actually what happens when you run a simulation. So magnetic fields couple the disk to the material in the plunging region, and they remove angular momentum from that flow. And so the material in the plunging region, which is where this is rotating far below the angular momentum that you would naively expect. Okay. And then finally, there's an effect related to emissivity. So in our numerical models, the density and the temperature and the magnetic field strength all increase sharply as you move inward toward the event horizon. And so if you look along lines of sight that pass closer to the black hole, then you see a higher intensity on those lines of sight. Okay, and that always happens on the sort of spinward side of the hole. So in, let's see if I can do this on this side in this case, and then if I go to positive spin on this side in that case. So these geodesics are always closer to the hole at closest approach. Okay, so there are a number of factors that contribute here. And now I just want to show you what emerges from the simulations when you include all these effects in a self-consistent way. Okay, so this shows a set of averaged images, time-averaged images versus spin. And there are two sets of models here. And one are called MAD models, and one are called sane models. So is everybody familiar with this? Yes, but no. Okay, so I'll explain it. So MAD stands for magnetically arrested disk. So these are models with a very strong magnetic field, which plays a role in breaking the plasma as you get close to the event horizon. These models are, this is a Ramesh Narayan term, standard and normal evolution models. And these have a relatively weak magnetic field, small correlation lengths for the field. And so they look more or less like standard thin disks, except that you still have this coupling between, magnetic coupling between material in the plunging region and the outer disk. Okay, so what you see here is a survey over spin, and you can see that the MAD models for the negative spin look like this. They look like the toy model I just showed you, no accident. And for very positive spin, the bright part is on the other side. Okay, so this tells you that the sense of the asymmetry is related to the spin. And in particular, you can see that there's almost no asymmetry here in the MAD models in the middle at zero spin. And then the amplitude of the asymmetry increases in either direction. Okay, now these are the guys that we think best fit the data for M87. So these have polarization characteristics, which are more like the polarized images. The sane models don't do quite as well, and they don't do quite as well in reproducing the jet power. And you'll also see that they look slightly different. So these are rotating faster in the plunging region. And so it turns out that the sort of zero asymmetry point is shifted toward negative spin here. Okay, so slowly rotating MAD models, you know, the point of zero asymmetry is right in the middle, or minimal asymmetry. And then for sane models, it's a little over here, maybe minus 0.5 or somewhere in between these two sampling points in our models. Okay, so so these are time averaged and actually averaged over some model parameters as well. Individual images fluctuate over time. So the amplitude of the asymmetry changes by quite a bit from snapshot to snapshot in the simulations. Okay. So here's a plot that shows that time evolution. This is that asymmetry amplitude, which is the ratio, the amplitude of the first Fourier component to the zeroth. And this shows the distribution of those amplitudes over time. So what we're after really is this distribution. And to get that, we have to take multiple samples of M87, which is one of the reasons we've gone back again and again to look at M87. Okay, so more samples means we can constrain this distribution better and obtain stronger constraints on the models. Okay, so again, one of the key points here is that the asymmetry increases toward higher spin, absolute value of the spin parameter A. And then the next point is that the distribution of these spins looks like this. So now we've gone in to each of the models, we've looked at the time series, and we've assembled a distribution function for the asymmetry at each value of the spin. And so on this plot, we have the spin down here, the asymmetry magnitude on the vertical axis, and then two of the measurements from 2018 and 2017, shown here with error bars. And one interesting point here is that neither of these are close to the mean asymmetry you expect for a zero spin model. Okay, so let's suppose that we go back and we gather more data. We make a number of measurements that lie in between here and here. Then we can look at the distribution of data points. We can do something like a KS test to ask what the probability is that that's drawn from the spin zero model. And potentially with a few more years of data, we can show that spin zero models in this model set are inconsistent with the data. All right, so the data could soon be inconsistent with spin zero. Again, this is the median value of the asymmetry, and this is the 90th percentile, and this is the 10th percentile. So you can see there's quite a bit of fluctuation over time. All right. So the next feature of this has to do with where this peak emission is. So what is the position angle of this m is equal to 1 Fourier component with respect to the projection of the spin on the sky? And you can see that whether the spin is positive or negative, that peak is either at 3 o'clock or at 9 o'clock. So it's always perpendicular to the projection of the spin vector on the sky. And that suggests that, interestingly, we can measure the spin direction as well as the spin magnitude if these models are correct, which is why it's important to build good models of these sources. Okay, so here, I just want to emphasize this. The accretion flow angular momentum is up on these plots, and the projection of the spin vector is up over here and down over here. So the bright spot is always on the approaching side of the black hole. So you just right-hand rule. All right. This is my favorite Feynman quote. I'm sure you've all been to the used car salesman talks. So we're not selling used cars, or like the guy who came to my door the other day trying to sell solar panels to houses that already have solar panels across the entire roof. So there are many potential issues with models here. And most of them have to do with a physical issue, which is that the material that's flowing onto the black hole is not rigorously described as a fluid. So it's a high temperature plasma, high temperature low density plasma, and it's collisionless. And that means that the Coulomb mean free path to collisions is hundreds of thousands of times the size of the black hole. And so it's not obvious that you can model this as a fluid. Now, things are a little more complicated than that. So I would say that the current best understanding is that when you have a turbulent flow like this, it drives the plasma toward a state where there are kinetic instabilities, so Larmor scale instabilities. And those Larmor scale instabilities produce small fluctuations in the electromagnetic field, and the particles can scatter off those fluctuations. And so that provides an effective mean free path for the particles, for charged particles in the flow. And that seems likely to be small compared to the size of the event horizon. So these may well be treated as a fluid after all. But that is still, I would say that is still under study. And there are many ways in which these collisionless plasmas could still deviate from a relaxed fluid. So one of the most important, which we think absolutely occurs, is that the ions and electrons don't need to be at the same temperature. So these are almost certainly two temperature flows. What we do in our models is make kind of an educated guess as to what the electron temperature should be, but there's no firm foundation for that guess. So typically what we do is adjust the parameters associated with that in order to match the observations. So we set those empirically. Yet another way in which the models could fail is in the assumption of a thermal distribution function. So you all learned at your mother's knee that synchrotron radiation is non-thermal. It's likely that there's a non-thermal component to the electron distribution here. So we know that there are limits on that, because if all of the electrons were in a non-thermal component, we would overproduce the infrared radiation that's observed from the galactic center. And so for the specific case of the galactic center. So the infrared to millimeter colors depend on sort of the ratio of thermal to non-thermal radiation. And that provides some, thermal to non-thermal electrons. So that provides some limit on the non-thermality. Okay, so there's other issues with these simulations, including the boundary conditions, the initial conditions, and we're attempting to survey those and understand exactly what all the implications of those are. But I think, the toy models produce an asymmetry that scales this way, and the full-up simulations, they're sort of the best we can do, provide this relationship between spin and asymmetry amplitude. And I think we just have to keep going and comparing the simulations with the data, and perhaps we can measure spin with that. And that speaks directly to the issue that I raised at the beginning about how is the jet powered in M87 and in other extragalactic radio sources. And the best bet model, I would say, is the so-called Blanford's-Nyack model, in which the jet is powered by tapping the spin energy of the black hole. And one of the predictions of that model is that the black hole should be spinning at the base of M87's jet. And so measuring the spin is a key step in testing the Blanford's-Nyack model. Okay, so I'm basically done. EHT future, we're going to do multi-frequency observations, higher resolution with those, and potentially movies. So next year, if our proposals are successful, it'll be a few years before I'll be able to show you a movie, but that's on the horizon. There actually was a movie in the 70s called The Black Hole. Did anyone? It was a Disney movie. Okay. Dating myself. The ring asymmetry is accurately measured for M87. So this is one of the most obvious features of the images. And we think that you can use it to draw inferences about the spin magnitude and the spin direction projected on the sky. And that's it. Thank you.
We have time for questions. I suggest if you ask questions, raise your hand and use the mic. For those who are either in the conference room or online, please raise your hand on Zoom. And okay, questions. Rachel.
Thank you, Charles. This is very exciting and beautiful. So again, as an outsider to this field, I feel like I've seen images and predictions from these kinds of simulations for at least a decade or so. So what is new and improved and better about these, this in-prep work that you were presenting? What have been the significant improvements recently in your work?
Yeah, so we have a new model set that we're using, which we think is better than the old model sets. It's got higher resolution. We ran it on Frontier. It also includes a survey over spin, which is much denser than what we were able to achieve in the past. And that's really the key advance.
So you got that really nice.
So we got, yeah, exactly. So before we had minus 0.9, 0.5, 0, yeah. And so that's the key advance there. And then there's an aspect of the physics which we think is better in the current set of models, and that has to do with the adiabatic index. There's a famous result in these trans-relativistic plasmas where the electrons are relativistic and the ions are non-relativistic, that the adiabatic index is 13/9. Okay, so this comes from having an adiabatic index of 4/3 for the electrons and 5/3 for the ions, which are non-relativistic, and then you combine them appropriately. And it turns out that's the wrong way of thinking about this, I would say. We think the electrons are much cooler than the ions, and so it really should be the ions which control the adiabatic index. They're providing all of the pressure support. And that changes the temperature profile inside the accretion flow from what it was before. And that concentrates emission deeper in the potential. Yeah.
Charles, you mentioned the fluid approximation and going beyond two temperature fluids, collisionless, and you have two black holes that you said you start. Which one's closer to the fluid approximation?
Yeah, I think they both have ridiculously long mean-free paths to cool and scattering. So I don't think we're in a comfortable regime with either of those. Yeah. So they're interpreting either of those sets of observations is going to require a trustworthy model for the plasma. Yeah.
So a route to getting spin from the larger scale properties of the jet and comparing that with simulations and what you now know about the conditions of the base?
Yeah, so it's really hard to draw inferences from the structure of the jet. And that is because of the problem of identifying the emissivity in the jet. So when you go farther out, the field gets weaker. So when you're observing in a single band, 230 gigahertz, that means you need larger and larger Lorentz factor to produce the 230 gigahertz emission as you go out. And so you're moving from sort of the core of the distribution function out onto the tail. And you can manipulate the tail in all kinds of ways to produce whatever total intensity structures you like out in the jet. Now, we have some ideas about what might happen in the jet, but I think all the predictions are less secure for the jet. Now, there's one way in which one could use the jet, I think. So some of these models are retrograde, which means that the accretion flow is going one way around the black hole, and the black hole is going, let's see, this way, and the black hole is going the other way. Okay, so let's suppose we could make a movie of the material around the black hole, 230 gigahertz, and correlate it over time to identify which way it's rotating. So we've developed a way of analyzing the data that should allow us to do that. Now let's suppose we make a movie of the jet and that we can identify in that movie which way the jet is rotating. If the disk is rotating one way and the jet is rotating the other, then we're done. It's Blandford-Nyack, because there's no other reason for the jet to be rotating in the other direction. We don't know which way things are going now. And I would say that some of the models that are retrograde are slightly favored by the data. So that's an exciting possibility. It's a live possibility.
Okay, we have Lorenzo.
You're certainly aware of this. Maybe something that you are expecting to be asked from me. So if you were to take your ring model, can you mess with the isotropy of the distribution function arbitrarily and maybe invert this correlation of the amplitude and the spin?
Yeah, possibly. I've not done that. So you can do all kinds of things to that model. So you can change the angular momentum. You can change the inclination somewhat. There's a whole set of parameters that you can use in the toy model. Yeah. But I've not done that. So I'm very interested in what happens in that case. But we haven't explored that yet.
Is it really possible to distinguish if it is really Blandford-Nyack launching the jet, or, for example, just the twisting of the field line from the black hole? Because in principle, even a neutron star with field lines that are attached to the surface by rotating would build magnetic pressure and actually be off than the jet. And even with Blandford-Nyack, just from energetics point of view, you get a maximum kind of a boost of, instead of 100%, 200%. So just a factor of 2.
With Blandford-Nyack? No, I don't think that's, I'm not sure I agree with that. I'm not sure what calculation you're referring to.
So you can get even more than 200% in energy.
Okay. That's what you mean by boost. I thought you meant the Lorentz factor.
No. I was not speaking about the Lorentz factor, but just to the fact that you can extract more energy than you originally had there because you take the spin of the black hole, but that is like a factor of 2-ish.
Yeah.
So.
Yeah, I don't think that doesn't excite me very much. So the way this is usually posed is it Blandford-Nyack or Blandford-Payne? So which of Roger's collaborators gets the credit? And I think most people who run these simulations believe that it's Blandford-Nyack. And the reason for that is that the field lines that run through the disk, which are the sort of Blandford-Payne field lines, tend to produce outflows that have Lorentz factors of sort of 2 at most. Whereas on the field lines that go through the black hole, which are very clean, they've been sort of vacuumed out by the infall onto the black hole. Those, are almost pure pointing jets, and probably are moving at very high Lorentz factors. So there's like a pulsar wind almost.
Yeah, I agree. So in this case, just Blandford-Nyack is a synonym of field lines being anchored to the black hole, but not really requiring energy from the endosphere of the black hole.
Yeah, well, so they do acquire energy from the ergosphere, or you could say that's what's being tested, whether there's frame dragging of the field lines. But at least in all the simulations, they're frame dragged, and that produces sort of a torsional Alfvén wave that moves out along the field lines, that carries the energy. Yeah.
Carrie.
Can you give me a sense for how generic these results are? Like, you're looking at a single system, and like how much do you expect these results to apply more broadly?
Right. So this allows, thank you for asking that, because this allows me to make a little plug for BECS. So we think these are pretty generic. M87 and Sagittarius A star are both seemingly well modeled by these simulations like this. And those range over a broad range in mass, so factor of 1,000 in mass, and factor of more than 1,000 in Eddington factor, Eddington ratio. So we think this is a pretty good model for low accretion rate flows. And one possibility with BECS is resolving more systems. So we think there are about 10 additional systems that could potentially, whose rings could potentially be resolved by Bex. And this says that if you can do that, you can potentially measure the asymmetry and the direction of the asymmetry, and therefore constrain the spin and the direction of the spin with respect to the parent galaxy, which I think would be super interesting. I will say that the magnitude of the asymmetry depends on inclination, though. So in M87, we think we have a pretty good handle on the inclination, under the assumption that the jet and the spin of the black hole are coaxial. Okay, so that's a key underlying assumption. In other systems, we don't really necessarily know what the inclination angle is.
We have time for one quick last question.
Yeah,
Yeah.
actually, to that point, so without constraints from the jet, is there in principle an observable that can constrain the inclination from here? Like when you say magnitude of spin, that's magnitude of spin transverse to the line of sight, I imagine.
It's just the absolute magnitude of the spin vector. Yeah. So are there other methods of, let me pretend that the question was, are there other methods of measuring spin? And the answer to that is potentially yes, but only with Bex. So you need that high resolution to resolve some of these narrow ring-like features, and then the shape of those features can constrain the spin.